Hello guys, here we are back at it again. 2.8 Subspace of Rn. Before we get started, I hope everyone is doing well. so, we're skipping a lot of sections in chapter 2. Um, um, so in chapter 2, we are just going to do what we have left is 2.8 and 2.9. In this section, we will be looking at a lot of the definitions and theorems of the fundamentals of linear algebra. Right, and let's get started. So have your notes ready. You should be able to download it from Blackboard. So if you look at the first definition, a subspace of Rn is any set H in Rn that has three properties. Okay. All right, so subspace, it needs to satisfy three properties. First, that we want our zero vector to be in the subspace H. Okay, and B, for each U and V in H, the sum is also in H. So this is what we have. U is in H, V is in H, then U plus V is also in H. Okay, and the last one is that the scalar multiple of a vector U in H is also in H, right? So if U is in H and C is some scalar, some real numbers, right? Then CU is also in H. Right? Now, if a set satisfies these three properties, then it can be called as a subspace of Rn. Okay, let's look at the first example. Okay, example 1. Right, we have V1, V2 in Rn, and we want our H to be called the span of V1 and V2. Right, remember the span? Span means all possible linear combination of V1 and V2. And we want to show that, then H is a subspace. Oops. H is a subspace of Rn. Okay, and we're going to show that real quickly. And in order to show that H is a subspace of Rn, we just need to show these three properties, right? So first, we want to show that the zero vector is in H. Now, that's very easy, right? We can just do that 0 times V1 plus 0 times V2. Now, notice that each one of them is a scalar multiple of V1 and V2. That means these two are also in the span. And that is equal to 0, the zero vector, which is also in H. Okay, so we've shown that, okay, the zero vector is in H. That's pretty easy. B, V1 and V2. All right, so we want to show that for some vector U and V in H, we want to show that they're also, the sum of them are also in H. All right, so U in H. Right. So if U and V, they are both in H, means U is a linear combination of V1 and V2, right? U is some S1 times V1 plus S2 times V2, right? That's the definition of being H, being in the span of V1, V2 means you can write it as a linear combination of V1, V2, where S1 and S2 are just some scalar, right? Similarly for V, I can also write V as T1 times V1 plus T2 times V2, right? So U and V, they're both vectors in our set H, which is a span of V1 V2. Then we can write both U and V in this form, right? In the linear combination as V1 and V2. And then we want to show that U plus V, they are also in H, right? So U plus V is S1 V1 plus S2 V2 plus T1 V1 plus T2 V2. Right, and let's reorder these a little bit. So I can write this as S1 plus T1 V1 plus S2 plus T2 V2. And notice what we have here is again another linear combination of V1 and V2 because S1 plus T1 and S2 plus T2, they are both just scalars, right? So here we can write U plus V as some linear combination of V1 and V2, and then therefore we're done, right? U plus, we know that this whole thing is in H, right? Right, now that's the second part, showing that adding vectors, they are still within the set H. Now C, that's a pretty easy one, right? So let's let U be V1, oops, S1 V1 plus S2 V2. Then some scalar multiple C1U is going to be CS1 V1 plus CS2 V2. And again, if you notice, these are again just some scalar, right? C is a constant, some scalar. S1, S2, they are scalars. So these two things multiplied together, that's just another scalar. And then there we have it. We also still have some linear combination of V1 and V2. That means we can say that this whole thing is in H. And then we're done, right? H is a subspace of Rn. All right. All right, now let's proceed with definition 2. Let's look at definition 2 together. The column space of a matrix A is the set call of A of all linear combination of the columns of A, or as we can understand it, let's say we know that if A, the matrix A, it consists of many different columns, let's say A1 up to AN, right? Then the column space of A is essentially the span using all the columns. Okay, so the column space of A, basically it's all possible linear combination using A1 to AN. Okay, so let's say if we say X is in the column space of A, then X can be written as some linear combination of A1 to AN, like this, right? So S1 A1 plus S2 A2 plus dot 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 plus SN AN, right? For some S1 to SNs in R, in real numbers, right? So any basically, if you have a vector in the column space of A, you can get this vector by performing linear combination using all the columns of A. right? The A1s to AN. All right, the next one, definition 3, we have the null space. Okay, so let's take a look at the definition together. The null space of a matrix A is the set null of A of all solution of the homogeneous equation AX equal to 0. Okay, so to put that in simple term, the null space of A contains all solution to the matrix equation AX equal to 0. Okay. Now, another way to describe this is, let's say, let some vector x be in the null of A. Then, for sure, we know that AX is going to equal to 0, the 0 vector. I want to be a little specific here. Okay, so the null space contains all the solutions to this equation right here, AX equal to 0. The null space is actually very fun to work with, and they're very easy because everything in this set, null of A, is always going to give you 0. You can think of this as like a group of people, and then whenever you ask them question, they always give you the same answer, right? So whenever you see something has to do with the null space of A, you immediately can think of this equation right here, right? AX equal to 0. All the x's, all the vectors in the null space is going to give you this equation. Okay. Now, let's take some time and prove that the null space of A is actually a subspace of Rn. And this is actually theorem 12 from the textbook, but it's pretty easy to prove because we just need to show that the null space of A is a subspace, right? And then we talked about the definition of subspace in the beginning of this video. We have to satisfy those 3 properties, right? Having the 0 vector, conserve under vector addition, and under scalar multiplication. Okay, so let's do that. Okay, show the null space of A is a subspace of Rn. Okay, so first, show the 0 vector is in null of A. Well, what's A times 0? It's 0, right? So here we know that this vector, right, that is in the null of A because, well, it satisfies the equation AX equal to 0, right? Well, this is like the trivial solution. Of course, when you multiply by 0, you always get 0. But that's the nice thing about null space, right? We get easy answers and then we get complicated answers, right? So in this case, we have the easy answers, right? Where this 0 vector is in the null space of A because it makes everything equal to 0, and then we can satisfy the equation. Okay, now B. Oh, why is it red? Let me change that. Okay, so B, I want to say that suppose U and V are in the null space of A. Right? We want to show that U plus V is in the null space of A as well. Okay, so here, here we are assuming my pen is acting a little weird. Okay, here you go. Okay, so here we can assume that U and V are two vectors in the null space of A already, right? We're assuming that this is true. We want to show that this is true as well. Okay, so U and V in the null space of A means that AU is equal to 0, and then AV is equal to 0. Now, if we can show that the matrix A multiplied by the vector U plus V is also equal to 0, then we're done, right? So here we go. And this is very easy as well, right? So proof A times U plus V. And by matrix multiplication, we can rewrite this as AU plus AV, right? And we know what AU and AV are, right? Up here, they are just two big zeros, right? And zero vectors plus adding together gives you a 0, right? Therefore, we can say that U plus V is also in the null space of A. Okay, very easy, right? Okay, now the last one, C, we want to show that scalar multiple of some vector in null space is also in there. Right? So let U be in the null space of A. Show that CU is also in the null space of A. Right? And then we can always do this by definition. Right? So A times CU, I can rewrite this as C multiplied by AU, right? Since C is just a scalar, I can apply the associative properties, which is taking the scalar C, put it on the outside, right? And then we know that AU is just a 0 vector, and then any scalar multiple of a 0 vector is a 0 vector, right? There you go, we're done. CU is in the null space of A. Okay, therefore, null space of A is a subspace of Rn. Right? Okay, so let's spend some time talking about the dimensions. Right here, we're saying that null space of A is a subspace of Rn. Now let's go back to definition 3 and take a look at the whole thing again. Right, so here we go. The null space of a matrix A is a set of null of A of all solutions to a homogeneous equation. All right, to put in an easier term, right, all of the vectors in null space of A satisfies the equation Ax equal to 0. And here we go. When A has n columns, the solutions of Ax equal to 0 belong to Rn. Now, remember that we are going to multiply A and X like this. Right? So Ax, which is A1, A2, up to AN. Right? So let's say we for our matrix A, we have n columns like that, right? A. And then X, our X is going to have the same number of entries as the number of columns in A, right? So I'm gonna have X1 up to Xn. Right, so that's what we're talking about. If the matrix A has n columns, then our solution or our vector or the X is going to be in Rn because we are going to have n entries in order to multiply it with the matrix A. Right, just like this. Right? So this thing is in Rn. All right. Last definition, we're going to look at bases. Okay. So let's take a look at the definition on the notes together. A basis for subspace H of Rn is a linearly independent set in H that spans H. Okay, so this is very a little confusing, I guess. So let's say I have a subspace H, right? That's a subspace of Rn, right? So this notation kind of like belongs to without the middle line. This is for subspace inclusion or subset inclusion. Right, so H is a subspace of Rn. Then let's say the basis, the basis of H is the collection of A1, AN, right? Something like that, right? So if the basis of H is this, that means H can be written as the span of A1 to AN. Right? Now, this is, again, very vague because we're using arbitrary dimensions and the vectors. So let's look at it in the simple term. Right? Let's look at R3. Right? Now, we are very familiar with R3, right? We have three x's, x, y, and z. X, y, and z. Okay. Now, as we talked about this in class many times, right? We are living in the three-dimensional world. That means there are three directions we can go, right? Like that. We can go along the x-axis, along the y-axis, or along the z-axis, okay? So these three axes actually forms the three standard bases. They are called E1, E2, and E3, right here, E1, E2, and E3. And what they are respectively is E1 is 1, 0, 0, right? You have 1 in the X entry, and then E2 is 0, 1, 0, and then E3 is 0, 0, 1. Okay, so these are the standard vectors along the axis, and the standard bases. Right, so we have three vectors that point in different direction. So we can say that when we span E1, E2, and E3, we get R3, right? Because we can get to any point in R3 by doing E1, E2, or E3, right? However many times, right? The linear combination of E1, E2, and E3. So when we have this, we can also say that, which is basically the same thing as saying that the span of E1, E2, and E3 is equal to R3, is by saying that the basis of R3 is E1, E2, and E3. Okay. So if we span the basis, we will get back to the whole dimension, right? R3. Now we can also increase our dimension, right? So let's say I want to find the basis of R4, right? Then we know that we can span E1, E2, E3, and E4, right? And then we'll get R4. Right? Now the E1 to E4 here, they are a little different than the ones that we looked at earlier. Right, the E1 here is going to be 1, 0, 0, 0. Right, we're going to have 4 entries now instead of 3 because now we are working in terms of R4. Right, so E1, E2, E3, and E4, like that, right? And then we can say that the basis is the collection of all these, right? Because we can span these 4 vectors to get to any place in R4. Now, in this case, we say any place in R4, but R4 is actually imaginary because we cannot actually visualize R4. But in mathematics, this is how it will work, right? Each row represents some dimension, right? 1, 2, 3, and 4 dimensions, right? So we have a 1 in each one of them, row 1, row 2, row 3, and row 4. And that's what makes the standard basis so nice, because we can easily find a basis for R to in any Rn. Right? We just need n many standard basis vectors, right? E1 up to En, and then we can span Rn. All right, next let's look at our last example, example 3. We want to find a basis for the null space of the matrix A. Right, A is, let's see, -3, 6, 1, -1, 1, and 7, -7, 1, -2, 2. Oops, what happened here? -2, 2, 3, -1, and 2, -4, 5, 8, -4. Okay. All right. So in order to do this, we're going to write this in write ax equal to 0 in augmented matrix form. All right. So -3, 6, -1, 1, -7, 1, -2, 2, 3, -1, 2, -4. Whoops. -4, 5, 8, -4. And then we get a bunch of zeros, 3 zeros on the right. Okay. Now, by elementary row operation to reduce row echelon form, we will get this 1, -2, 0, -1, 3, 0, 0, 1, -2, 2, -2, 1, 2, -2, and then 0, 0, 0, 0, 0. Okay, and then again, we get a bunch of zeros on the right hand side here. Okay, so this is augmented matrix in reduced row echelon form. And let's convert this back into equations. Now, as we know that the columns in the left-hand side of the augmented matrix, they represent different variables, right? So let's convert the first row into equations first, right? So we have x1 minus 2x2, right? That's a 0, so 0x3, and then minus x4, and then plus 3x5 is equal to 0. And let's look at the second one. I have x3 plus 2x4 minus 2x5 is equal to 0. And then since the third row is all zeros, we don't have to worry about them. So these are the two things we have to work with. Actually, let's just put a 0 is equal to 0 for our third row, which doesn't give us any other information. All right. So now we want to write our solution, right here, x1, x2, x3, x4, and x5. And we want to solve for each one of them. Okay. All right. So x1, let's take a look at where we have x1. So x1 we have here. So we can move these three terms, the minus 2x2 minus x4 plus 3x5 to the right-hand side. And then we can write x1 as 2x2 plus x4 minus 3x5. Right? And the same thing for x2s, right? So we have to move everything over. So Actually, so let's come back to this form right here. Notice that the pivot columns are the first and the third column, right? So remember the pivot column, right? You hit the first non-zero column, right? So we have the first column and the third column, they are the pivot column. So we only need to worry about x1 and x3. So in this case, we took care of x1 and x3. We can rewrite that as negative 2x4 plus 2x5. Now you might ask, what about the rest? What about x2, x4, and x5? Now notice that x2, the second column, the fourth column, and the fifth column, they are not a pivot matrix. So pivot column. So for x2, x4, and x5, they are just free variables. So x2, we can just use x2, x4, and x5. Now notice that x2, x4, and x5, they are our free variables, quote unquote. Right, so we can rewrite x1, x3 using those three variables. And that helps us identify what we have here. And I'm going to rewrite this in a different form. I'm going to write this as x2 times 2, 1, 0, 0, 0. So notice that I have 2x2 in the first row, 1x2 in the second row, and zeros in 3, 4, and 5. Okay, I'm going to write it as a linear combination. And then next free variable is x4. Right, so I'm going to write x4 right here. Right, so I have 1, 0, negative 2, 1, 0. Plus x5, negative 3, 0, 2, 0, 1. Right here. Okay. So far what I've done is convert this thing right here into a linear combination, break it down into a linear combination using these three vectors, right? And then those weights are x2, x4, and x5, which are our free variables. And what's nice about this case is that these three vectors, right? Let's call that u, v, and w. These three are going to be the basis for our null space, right? So the null space of A can be written as the span of these three, u, v, and w. Okay, and that's how you find the basis for a null space of any matrix, right? First, you write it in augmented matrix form, reduce that to echelon form, find your pivot column, and then solve for those variables using the other variables. And then whatever is left, those are your free variables. Rewrite these as a linear combination using your free variables, and then the resulting three vectors right here, the u, v, and w, right? You don't necessarily have to have three. Sometimes you have more. And these are your bases for the null space of A. Now remember that we talked about the bases, right, which are the three vectors that makes up the whole thing, right? So if we span the bases u, v, and w, we get the whole thing, which is the null space of A. Okay? And this is how you find a basis for a null space of matrix. Now, if you keep going on the notes, the last theorem, theorem 13, it says the pivot columns of matrix A form a basis for the column space of A, right? So furthermore, we found that these two, column 1 and 3, right? These are our pivot column. That means the original two columns, right? They are the basis for our column space. Basis for the column space of A, right? Just some extra info thrown in there to help us will work with the column space. Okay. But I don't think we're going to focus too much on the basis for column space for now. For now, we're going to focus more on the null space and the basis. Okay? So make sure you understand the definition in the notes, right? First, we have the subspace, very easy to check. The column space, which is just the span of the column, right? And null space from definition 3, and then the basis from definition 4. Right, so total we have 4 very important definitions from this section, and just take your time, try to understand what these 4 definitions mean. I know this can be these are a lot of information thrown at you, but just take your time and look at different examples, either in textbook or on YouTube. They have some very nice example there to help you understand this concept. Okay, so I'll be making the videos for 2.9 over the weekend, and then I'll try to post it on maybe Saturday or Sunday night. All right, thank you guys, and see you next time.